So in the previous video, we were talking about 30, 60, 90, 45, 45, 90 triangles. If you haven't watched that one, please watch that one first. So over here, I'm showing some nested similar triangles, similar right triangles. And I just want to talk about some of the sort of constant ratios we have. So let's say, for example, that the measure of angle A is 30 degrees. We know from our 30, 60, 90 relationships, if this side length is 2, this would be 1, and this would be 1 root 3, okay? And the next nested triangle, if this side length is 4, this would be 2, this would be 2 root 3, and I can do one more. And this is because all 30, 60, 90 triangles are similar, and we know that these triangles in general, any nested triangles, are similar by AA similarity. So if this is 6, this would be 3, this would be 3 root 3. Well, something interesting about this is if I want to think about some certain relationships that appear in this kind of triangle, this angle, in reference to this angle 30, this side is called the opposite side. So this 1, 2, and 3 side. This side down here is called adjacent. Okay, adjacent means next to or next to the angle. And then this one up here is called the hypotenuse. And you can think of hypotenuse. I totally misspelled that. Okay. So you can think of a hippo kind of going up here. I can't really draw a hippo, okay. So anyway, he's kind of going up the up the ramp. Okay. So if I think about some of these ratios, if I think of the side length of opposite divided by hypotenuse, what this ratio would look like. If I look in, and I could also compare adjacent to hypotenuse, and maybe opposite to adjacent side in those different triangles that I've created. I may look at, let's go back to that purple. The opposite to hypotenuse side would be 1/2. The adjacent to the hypotenuse would be root 3 over 2. And the opposite to adjacent would be 1 over root 3. Okay. And, okay, that's interesting. I could compare that now to, in the blue triangle, what those values would be. And I see that this is going to be 2 over 4. Adjacent to hypotenuse would be 2 root 3 over 4. And this last one would be 2 over 2 root 3. And then lastly, I could do the same thing for the green. Okay, so this would be 3 over 6, 3 root 3 over 6, and this one would be 3 over 3 root 3. Okay, what we're noticing here is that all those triangles, because they are similar, this ratio 1/2, 2/4, 3/6 all simplify to 1/2. That it doesn't matter the size of those, the size of the triangle, that ratio stays constant if that angle is 30 degrees. So we call this ratio here sine of the angle. Sine is opposite over hypotenuse, and that constant ratio, in this case of 30 degrees, is equal to 1/2. It doesn't matter what size triangle I have, that relationship, the sine of 30 degrees, will always be 1/2. Adjacent to hypotenuse, we see that that will always simplify to root 3 over 2, right? That will be a 2, that will be a 2. So the cosine of 30 degrees will always be this ratio, always simplified to this number, root 3 over 2, and that's an exact value. And I could do the same thing down here, opposite to adjacent. I see that that's going to simplify to 1 over root 3, or if I rationalize that, to root 3 over 3. Okay, This constant ratio is tangent of 30 degrees is equal to root 3 over 3. So these right here is kind of the fundamental idea of trig ratios. Like sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent, that those are constant ratios for every given angle that we have. So over here, those are constant ratios. It doesn't matter what we have here, that no matter what this angle is for a given angle, that ratio is going to be constant for that angle. So you may want to put these in your notes, and then let's take a look at the implication of some of these. So over here, if I have a triangle ABC and it says solve the given triangle, this word solve means find all the missing values. A couple of things I could do here. So I know that the measure of angle A, this notation is pretty poor, the measure of angle A is 24. We know that we can easily find the measure of angle B, and I can either take 180 minus 90 minus 24, or we know if that one is 90, 90 minus 24 will be that angle, so it's 66 degrees. Okay, and I know that this hypotenuse is 15. So with the given information that I have, I know that this one is 24, this one is 66, this is 90, and this is 15. How do I find the other side length values? Well, I'm going to call this for now X, and I'm going to call this Y. So notice if I want to find Y, I need to use sine. Oh, can I mention something on the previous slide? So some of you have heard different ways to remember sine. An easy way to remember that is just remembering SohCahToa, sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. Some of you know some other ways to remember that. Okay, so here, if I want to find this height AC, I can say, I notice that I have the hypotenuse and I'm looking for that side opposite. So I could say sine of 66 degrees is equal to y over 15. And then I could multiply both sides by 15 to be able to solve. Okay. So if I take this here, now in your calculator, you want to remember or double check that your calculator is in degrees. Right now, you don't know much about radians, if at all, but it's important that you have it and you're checking that it's in degrees, okay? Right here, so 13.7, if I want to find x, I'm going to say x is the adjacent side, so I'm going to say cosine of 66 degrees is equal to x over 15, so times 15, and I can solve for that. 6.1 units. Okay. Down here we can do that similar. I just wanted to show one other thing. If I know that this angle is 36 degrees and A is 7, I could find the measure of angle A using that subtraction property, but I could also find it in a different way. I notice that the measure of angle A, if I had another side, which I could solve for in a minute, I could actually use the trig ratio to be able to solve it, and we use something called inverse trig values. So I might first solve for, say, this B side if I wanted. I'm going to call this Y. So just like we did before, I could say I have that adjacent side, so now I might use tangent of 36 because I have the opposite and adjacent side. Y divided by 7, multiply times 7, so I see Y is equal to 7 tangent of 36, and I get 5.09. So once I have that side length, I could actually use a different ratio. If I wanted to find the measure of angle A, I would actually have the opposite and the adjacent side would be different. So I could say tangent of the measure of angle A, the opposite side to A is actually that 7 value, and then Y we just found is 5.09. This right here has a ratio, and I can use this to solve for the measure of angle A. To get rid of this tangent, I'm going to use the inverse operation, tangent inverse, and that's exactly like the inverses we've been talking about. So I can take tangent inverse. Tangent and tangent inverse undo one another. So I have here the measure of angle A is equal to tangent inverse of 7 divided by 5.09. You can hit second tangent, and that will give you that tangent inverse operation. And I get that that measure is 53.98. So we see that's like 54 degrees. Okay. Two other questions that are really interesting here that are extending into some work that we're going to be doing. This says find the cosine theta and tangent theta. These are the ratios. If I'm given an acute angle and I know that sine theta is 5/13. So if I make a triangle, I don't know what theta is, but I'm actually just asking for what those ratios are. If I have theta here, I know that sine is 5/13. That's telling me that the opposite side is 5 and the hypotenuse is 13. You may remember I could use Pythagorean theorem, but this is a Pythagorean triple. And here this is a 5, 12, 13. So here I know that this side length would be 12. So here, if I want to find cosine theta, I'm asking for the ratio of those sides would be adjacent to theta, and hypotenuse would be 12/13, and tangent theta would be opposite over adjacent, which would be 5/12. So those would be those ratios. In the next one, if I have to actually solve for those values, here, I can do the same thing. This is theta. I'm told cosine is 12/15, so that tells me the adjacent side is 12 and hypotenuse is 15. I'm going to have to solve for that opposite side length. If I do that, I'm going to use Pythagorean theorem. So I can say like 12 squared plus b squared is equal to 15 squared. B squared is equal to 15 squared minus 12 squared. So that's 81. I'm showing plus and minus. We just remember here that when I'm finding length, obviously that's a 3, 4, 5 scaled up, but I'm just showing the process here. So b is equal to 9. So right here, I'm just showing this process, and we know that whenever I take a square root, I have plus and minus. When we're dealing with length, it's just the positive side. So now that I have that, if I want to find sine of theta, I'm going to say 9/15, which can be simplified, divide out 3. And tangent of theta, 9/12, I can again divide out 3. So here I have 3/4. Okay.